Assalamualaikum. Good morning.
Good morning, Doctor. Good morning, Doctor.
Okay. Can you hear me? Can you
Yes, Doctor.
Attendance will be taken after the class via online QR code. So please stand by. Where do we stop? Example 6. Hello?
Yeah, I think.
Right. So for example 6, for the system shown below, find the frequency and gain k for which the root locus cross the imaginary axis. Okay. For what range of k the system is stable. Okay. So from the given open loop transfer function, GS, which is equal to k s plus 3, s plus 1, s plus 2, and s plus 4. Okay. Okay. So first, the open loop, closed loop poles is 4. Open loop poles 4, which is 0, -1, -2, -4. Open loop 0 is 1, which is -3. Okay. So we find what do you call it? Uh, closed loop poles. Okay, as shown here. Can you see? Can you see that? Hello?
Yes,
Can
doctor.
Yes, doctor.
Yes, Doctor.
And then find the closed loop transfer function. Which is k s plus 3 uh, s plus what? I forgot. S plus 1, s plus 2, s plus 4. Then plus k s plus 3. So characteristic equation, by taking the denominator, s plus 3 equal to 0. Okay, as shown here. Okay. So you simplify this. Simplify. So you will get square, cubic, s power of 4. Okay. S power of 4 plus s cubic plus s square plus s equal to 0. Okay. So if we look at the slide, so it is there 7 s square 14 s square 8 plus k and plus 3k. Okay. Then you insert the coefficients of the characteristic equation, which is 1, 7, 14, 8 plus k, and 3k. Okay. And put inside the Roth-Lewis table. Okay. So I will do it. The coefficients, characteristic equation, 1, 7, 14, 8 plus k, and 3k. Okay, insert inside Roth-Lewis table. Okay, so I insert. Okay, this one, insert inside the Roth-Lewis table. S power of 4, s cubic, s square, s power of 1, s power of 0. Okay, can you see, guys?
Recording in progress.
Yeah.
Recording in progress. Recording in progress.
So s power of 4 is 1. 1. Off microphone, please. 7, 1, 7, 14, 8 plus k, 3k. Then this one, put 0. Okay. Hello, guys. 0, Hello. Okay. Then this one, how to do it? Is using the formula that I teach you last 2 weeks.
Yes, I determine.
Okay, so I change to another slide. Is negative what? 1, 7,
7,
1, 7, 14, 8 plus k, right? Divide by 7, kan?
yes,
Then simplify the determinant. 1 multiplied by 8 plus k minus 7 multiplied by 14. How much? How much, guys? 7 multiplied by 14. Help me.
98.
98. Minus 8 plus k. Correct? All divided by
Yes,
7. Can. So that's why you see in the what here,
determine.
see 90 plus k, 7. Actually, you can simplify. So you can simplify. Okay, can simplify. 98 minus 8 plus k, correct? Divided by 7. 98 minus 8 minus k, sorry. 98 minus k, So 90 minus k divided by 7. And then continue for s power of 1. You get minus k square minus 65k plus 720 divided by 90 minus k and 21k. Okay, guys. If you look at this, the concept of root locus says that the first column, okay, the first column of the root width must greater than 0. So the first column is here. This one, first column. Okay, this one we call it as the first column of root width, and it must greater than 0. 1 greater than 0, yes. 7 greater than 0, yes. And then the one that we mentioned here, 90 minus k over 7 greater than 0. 90 minus k greater than 0. So minus k minus 90, then k less than 90. That is the first one for the third row. Okay. So the fourth row is this one. Okay, minus k square minus 65k plus 720 greater than 0. So minus k square minus 65k plus 720 over 90 minus k greater than 0. Okay, this one. So we simplify minus k square 65k plus 720 greater than 0. This one multiplied by 0, 0, cross multiply. Then we change k square plus 65k minus 720 greater than 0. So please find the roots of this. Can somebody help and find the roots for k? K square 65k minus 720?
9.645.
9 point.
645.
The other one?
Negative 74.65.
Negative 74,
Mm.
Okay, so we go to the screen. Okay. So we chose K 9.65. Okay. So the range of stability is between 0 and 9.65. Range of K for stability. Okay, this one you already learned in the modern modeling and control. We just revised K greater than 9.65. Okay. So What do we understand of this range of K for stability? K is the gain. Okay. This K is the gain. V naught over V in is the gain. So if K, guys, is K equal to 4, is it stable or not stable?
Yes.
Stable.
Stable.
If K is equal to 10, is it stable or unstable?
Unstable.
Unstable. But if K is equal to 9.65, is it stable or unstable?
Unstable.
Salah?
Critically stable.
Marginal.
Oh my God.
Marginal or critical stable. So these three concepts you must digest and understand. And remember, all K values that in the range of minimum 0 and maximum 9.65 is stable, including 9.64, 9.63, 9.6, and so on. If K is greater than 9.65, 9.66 unstable, 9.67 unstable, 10, 20, 100 unstable. But if K equal to 9.65 is the marginal stable. Okay, please digest this concept because this is important for you to design the controller. Okay, so we use the K value, the marginal value, 9.65. We insert inside the even polynomial. So even polynomial is at S square, which is 90 minus K and 21K. Okay, so you construct the quadratic equation, 90 minus K, 90 minus K S square plus 21K, okay, equal to, so you insert the value, insert the K value, okay. So 90 minus 9.65 S square plus 21 multiply 9.65 equal to 0. Okay. Okay, you insert inside. Then you will get what is the equation? The quadratic equation. The quadratic equation will be 80.35 S square plus 202.7 equal to 0. Okay. And S is equal to what? Use your calculator. Plus minus J 1.59. Okay. Okay. Can? So if we plot the root locus, okay, we plot the root locus. Go to the screen, go to the MATLAB. Okay. G equal to K equal to 1. So S plus 3, guys, over S multiply S plus 1 multiply S plus 2 multiply S plus 4 closed. Okay. Can you see? Then R locus. R locus G. Okay, so we share the plot. Okay. Can you see the plot?
Yes.
Okay. How many root locus pass here? The open loopholes is 4, S power of 4. So that's why you have 4 root locus. Blue color, this one is what color? Cyan color, red color, green color. Cyan is a mix between blue and green, so we call it cyan. Okay. And intersection between the imaginary axis and root locus put grid. Okay. Oh, I cannot scan from here. I don't know why. Okay, maybe I have to close this one first. Okay, plot again. Okay, what is the value of the plus minus j? 1.49. 1 point. $1.59 plus j 1.59. Okay, so we share the screen. Can you see?
Yes, doctor.
There. So that is the point where the root locus cross the imaginary axis. You can see that the pole's value there is 0 plus minus j 1.6. Okay, we got 1.59, but by computer we got plus j 1.6. The real in front there 0.00466 actually is 0. Okay, so you can ignore that real is because it's very small. You just consider the imaginary axis there, 1 j 1.6. What is the gain value at this point?
9.8.
9.8. And the one that we get using the route twist is K 9.65. More or less the same. Okay. By computer, they are more accurate. Right. Okay. So far, understand? Okay, So online quite challenging lah. You relax, but you need to catch up very fast. So there are the plus minus J 1.59, one at the top and one at the bottom. Okay. And the asymptote line is 3, 60 degrees, 180 degrees, and 300 degrees to guide the root locus path according and not the border of the asymptote. Okay. This is by computer. Okay. This one more accurate. Plus J 1.59 and gain 9.65. See, different computer, you got different values based on the resolution of the your laptop lah. This one is a quite old laptop, so I get successful 9.65 and plus minus J 1.59. Okay. So the rule number 8 is the angles of departure and arrivals. So angles of departure is correspondent to the pole and angle of arrival correspondent to 0 can be calculated to further refine the sketch, okay, to make the shape of the root locus in the fine plotting lah. Used for complex open loop zeros and complex open loop poles. So the root locus departs from complex open loop poles and arrives at complex open loop zeros. Okay, because it follow the rules of the root locus, which start from poles, ended at zeros or infinity. And this angle actually can be found by using the angle property, okay, that been simplified. Okay, theta A, theta arrival, is the summation of angle all poles towards B minus summation angle of all zeros to B plus 180 degrees, while theta departure is summation of angles all zeros to A minus summation of angle of all zero to A plus 180 degrees. So that is the difference. Theta A arrival correspond to poles. Theta D, theta departure correspond to poles. Theta A correspond to 0. Okay, as mentioned in the first point there. So this is the A and B point. Okay, which is the correspondent situations of that formula. Okay, where in this case angle of departure, it happens at the uh, com complex conjugate poles here. Okay, is the complex conjugate poles, and angle of arrival occurred at complex conjugate zeros. Okay, theta 2 and theta 3. Angle of departure theta 1 and theta 5. Okay, so this angle theta 1, 2, 3, 4, 5. Okay, we'll refer to this formula of angle properties as mentioned below. Okay, just follow the formula, then you will get the angle of departure and angle of arrival. Angle example 7. So in this example 7, the unity feedback system find the angle of departure from the complex poles and sketch the root locus. So from here, in example 7, how many open loop zeros? 1, which is minus 2. How many open loop poles? 1, 2, 3, which is minus 3. And can you help me? S square plus 2s plus 2. What is the roots? Minus 1 plus J1, correct? Hello? Minus 1 plus J1, eh?
Betul.
Okay.
Benar.
Thank you. And then we plot. Okay. So we plot the root locus. Can see that three root locus paths: green, red, and lavender. Okay. The first root locus path, green and red, is complex conjugate poles ended at infinity. And the third one is -3 ended at zeros -2. So one root locus ended at zeros. The remaining two root locus ended at infinity. So we want to measure the angle of the departure occurred at the complex conjugate pole. We start with the on the top side, and then once we get the value, you just plus 360 degrees to get the bottom side. Okay. So angle of departure, as written there, angle of departure from the complex pole. So we use the formula. Okay, we measure the theta 1, which is the first complex conjugate poles, and then theta 2, the reciprocal, and then the 3, theta 3 is due to the zeros at -2, and 4 is due to the poles at -3, plus 180 degrees. And we get that the theta 1 is the angle of departure is 108.4, more than 90 degrees. Maknanya, meaning that the root locus path, the first one, the red one, it goes up to the infinity at the angle of 108.4. Okay, so that's how we calculate the arrival, departure angle. And then the final one is rule number 9, plotting and calibrating root locus. So all points of the root locus satisfied the magnitude and angle properties. That is a must. Then we want to locate points on the root locus and their gains. For example, when the root locus cross the line representing 20% overshoot. Okay, so the gain k, any point of the root locus is given by k 1 over the magnitude, as I show in the class how to calculate the gain k, using the formula on the whiteboard last time. So we go to the example 8 to sketch the root locus, okay, and then find the gain k at the j omega crossing, then find the break-in point, then find the angle of departure from the complex poles, and then verify it using MATLAB. Okay, we do it together. This is example 8. Open loop transfer function. Okay. So this is the plot. Okay. So plot is given. Okay. So you can see that the complex conjugate poles, the open loop zeros is 1. The value is -2. Open loop poles is 2, which is complex conjugate pole. Can you help me find the roots? S square minus 4s plus 13. Can you help me, guys? Minus what? S square minus 4s plus 13. Positive 2 plus minus j 3, Okay. Hello. Hello, guys.